all the stars and galaxies that we see might be remnants of that confluence of quantum mechanics and gravity during those very, very early phases of the universe. I'm Gerasimos Rigopoulos. I am a theoretical physicist working here in Newcastle University in the Department of Mathematics, Statistics and Physics. I am a theorist and I work in cosmology, which is the study of the universe as a whole. There was something about growing up in Athens is that there's nothing in the sky. Light pollution is so intense that the sky is just a red haze essentially. But you go to the beach, you're far away from the city lights and you see the sky, it fills you with wonder. And that's the thing that started me. I always want to understand what's in the sky, what the stars are and what space is. When I was in high school, I bought myself a college book about astronomy. But the thing that interested me most were the final chapters, where it was about the beginning of the universe, so the high energy physics and particle physics and gravity that we really don't understand. I slowly drifted away from observatories to paper and computers. So that was a path that led me to where I am now. It boils down to be fascinated by how the world works and trying to understand what's happening in the universe. The fabric of space is a metaphor that tries to convey the idea that space is not something rigid and always existing as you might intuitively think. It's not a stage in which things happen, but it's an actor. It responds to matter, and its curvature is actually what we understand gravity. So let me try to give you an example of what it means to curve space. So say that I want to measure the distance between these 2 points, between my hands. So what I would do is use some sort of yardstick. So I have prepared a yardstick here. So say that instead of using a meter, I get a few friends and ask them to join hands and ask them to connect these 2 points. Okay, so that's a very sophisticated way to measure the space. So how much space there is between these 2 points. And I have, 8 friends of mine that can hold hands and reach from this point to this point. Now suppose that I insert a planet between my hands and I drill a long tunnel through the planet, and I do the same experiment. I call my friends, ask them to join hands and go from one point to the other. Amazingly, what happens is that now my 8 friends will not be enough to reach from this point to this point. What has happened is that the presence of this mass of the planet has created more space, if you wish. So now my 8 friends are not enough to go from one point to the other. I need one more friend, let's say. The mass of the planet has curved space, created more of it, and now the distance between one point and the other is different from what it used to be. So space responds to matter. That's what we understand as gravity. All bodies in the universe, in fact, try to follow the straightest possible line they could as they move in space-time. But because massive objects curve, the straightest possible line for planets are in fact the orbits that we see. So what they're doing, they're trying to go on the straightest line possible, but in a curved space, that line is the orbit. When you move masses around, when you move energy around in general, the space-time geometry responds to that motion. And in fact, gravitational waves are precisely that. I have some massive object and I accelerate it around. What I'm doing is creating ripples in space-time that propagate outwards, and that's what we detect as gravitational waves. Gravitational waves were a prediction of Einstein's theory of gravity, general relativity. They are little ripples in space that propagate outwards. We know that they exist since the early 80s. There was a system of a binary pulsar, so you had 2 pulsars orbiting each other. The theory tells us that they should emit gravitational waves, which are ripples in space-time that propagate outwards. And as they do that, they lose energy and they get closer and closer to each other and they speed up. So by observing that binary pulsar back then in the early 80s, people were able to determine that indeed it loses energy at precisely the rate that the theory predicts. So we knew that gravitational waves existed since then. But in 2015, there was a momentous discovery by the LIGO observatory in the US, where we heard the gravitational wave passing through. And that was the result of 2 black holes colliding 400 parsecs away. They sent these ripples in space-time that went through Earth and allowed us to detect them. Now, there was a momentum discovery, first of all, because it was the first time we actually saw these ripples. We didn't infer them, we heard them. And secondly, this opens up a new window to observe the universe, because now we can hope to start doing astronomy with the gravitational waves. With gravitational waves observed, we've gone past the stage where we proved that they exist, we actually heard them, and the next step would be to try to use those gravitational waves to do astronomy, because they allow us to see things that cannot be seen in light. The feeling of understanding something, or truly understanding. So you're looking at the problem, you're trying to do a computation of what happens under certain circumstances, and you're standing there for months, and slowly the fog lifts, and at some point, there it is, there's the answer, it's clear. I think that feeling that you get by trying to understand something is what really drives me. I want to understand how the world works. It's almost like nature worship, if you wish. So I want to know what makes things around me tick.